I won't give like present machine learning talk, but all those things that I will be showing will be things that you can or actually are done using machine learning. So essentially my work is inspired by the development of output devices. And what I mean here is our displays and new additive manufacturing techniques like 3D printing. And they are not only getting higher quality, but they're also easier to use. And more importantly, they also give us new possibilities how we use them. And what I mean here is we have those new devices that allows us to emerge observers into virtual worlds. We have new additive manufacturing techniques which allow us to create those very sophisticated shapes and almost copy certain things or allow us to prototype very quickly or create very functional objects. And lastly, we can also combine those two worlds and we can use augmented reality, 3D printing all together to essentially augment the reality with the digital data. What is interesting is that when you look at those devices, they essentially come at different sizes, different prices, of course, but also what is important, they all have different capabilities. And on the other hand, in computer graphics, and not only there, we learn how to acquire digital content. So we have very high resolution cameras. We have also cameras that not only capture the images from one point of view, but actually capture images from nearby points of view, and those are called light field cameras. We also know how to scan and digitize physical objects, how to acquire the appearance information, and all this later is, for example, used for rendering images that often are indistinguishable from real photographs. And at the end, you can also apply any other techniques which essentially combine all this data and create new, very rich content. So essentially what I'm interested in is this thing. On one side, we have those different sources of almost unlimited digital input, and on the other side, we have very different output devices that we use nowadays. So the question is how we actually take this digital data and represent it on those different output devices. And what I do in my research is also I take into account the human sensory system, which in most cases is actually the final kind of receiver of the product of output devices. And what I realized over years, and not only me, maybe it's also clear that in this pipeline there are many bottlenecks that we are actually aware of. So first of all, on the digital content side, when we want to generate the content, there are huge computational constraints. And what I mean here is, for example, if you want to render images for VR or AR displays, it has to be very high quality. We have to render multiple images. They have to be high resolution, very many images per second. Then for example, on the 3D printing side, we have to address those shapes that consist of billions of individual, we call it voxels, where each voxel can be different material. And besides the limitation on the digital content creation side, we also have limitation on the side of output devices. And these, for example, include low resolution of those current devices, low temporal resolution, so current devices are mimicking the motion by showing discrete numbers of frames over a certain period of time, whereas in reality, everything happens continuously. For new types of devices, we have also some comfort concerns where they may introduce some fatigue or discomfort. And on the side of the 3D printing and additive manufacturing, anybody that tried in the past to print something knows that you're not always getting what you actually wanted to get. And the last thing is what is also interesting, we also have some inboard limitations regarding our sensory system. So starting with vision, in vision science, we have something basic like contrast sensitivity function, which pretty much describes which pattern we can see and which patterns we cannot see. And very relevant for new displays devices is the fact that our quality that we perceive all the time is not uniform, which means we see very high quality content in front of our, like in center of our vision, but everywhere in periphery it's pretty much blurred, but we don't notice this. And there's also certain illusions that we are not always aware of. So this figure, essentially, you may think that the top block is darker than the bottom one, but if I occlude this transition, you actually realize that those colors are exactly the same. So those are the limitations that actually are inborn limitations of our human sensory system. So what I'm trying to do in my research is essentially take advantage of all those limitations to have better translation processes. And what I do, I essentially study how the human sensory system works. I try to model it and include this knowledge into this translation process. So just to put this in a bigger perspective, in other research areas, there are people who do visual science and haptic science, and those people are interested in specific aspects of vision, of haptic perception, and reproducing certain phenomena. On the other side, we have a field of so-called computational display and fabrication. This topic became quite popular recently in computer graphics, where people essentially create a new display designs by stitching parts from different displays and running some computation to address them. And the same thing happens also in fabrication, when people essentially use the new digital fabrication techniques to come up with computational methods to create interesting results. So I'm essentially somewhere, what we are doing is somewhere in the middle. We still try to understand the perception, but what is different from what I showed on the left is the fact that we try to actually computationally model it. So we create models that can kind of mimic the way the human sensory system works. And on the other hand, we use this kind of idea of using computation and hardware limitations, and we put those pieces together, and what we create is so-called perceptual optimizations, which essentially take this knowledge of this perception into account and use this as a translation process to achieve the best quality possible. And this not only, this knowledge that we gain here is not only affecting this translation process, but also we can define the techniques that improve the content creation and also improve the hardware design. So essentially in the next some slides, I will try to convince you and show you some examples that quality experience can be significantly improved if we put those pieces together, meaning perception, knowledge, computation, and hardware design. And the very early project that I've been working on considered this problem of a gap between the resolution provided by the cameras or rendering systems and the resolution of the displays, where there is a huge gap in terms of resolution. So the idea was essentially to take very high resolution image and then show it, essentially do something to it, that when we show on the screen, it actually creates an appearance of it was really high resolution image. So we show it on much lower resolution device than the image is, but we still want to recreate this illusion of looking at high resolution image. And it turns out it's possible. You can exceed actually the physical resolution of the display device by decomposing this one high resolution image into multiple low resolution images and show it in this rapid succession on the screen. As a little disclaimer here, this works only for moving content, and maybe this will become more obvious when I show you how it works. So imagine that, and why it works. So imagine that you have 2 pixels on the screen, and we are looking at the screen, and we have some photoreceptors. We have more photoreceptors than pixels on the screen. Some photoreceptors are looking at the first pixel. Now, when we start moving the content, we as humans, we are essentially accustomed to following the moving object on the screen. So what happens is we move the object on the screen, and also our eyes follow. So now by altering the values of those pixels, what we can observe that after a certain time of time, after a certain time, our receptors received some signal over time, which is actually averaged by the human visual system. So at the end, each pixel, although at the beginning it was seeing the same pixel, actually at the end receives slightly different signal. And this is the means that we are using to actually addressing those photoreceptors individually. So now, having this idea, what we showed is that you can create a computational model that takes a bunch of images which are low resolution and predicts the image that we actually see. So this is some, you can describe it as some mathematical formula. This is not maybe very important. What is important is that you can invert this model. So what you can do, once I know the motion in the scene, and I know the image that I want to see at the end, I can optimize for the images that when I show on the screen, they create this illusion of high-resolution image. And this is just an example. So those are the 3 images that the method generated. And as you can see, you cannot really, maybe you can suspect what is there, but you cannot really tell exactly what's there. And believe me or not, if you show these images on the display and you move this image, you see this. And so you can see that there is a quite significant resolution enhancement. You actually can read the text. And I mentioned that this works for moving content, but if you think about videos, there is already a motion in those scenes. You can use it. And more recently, we also showed that we can run it for those new devices where we had head motion, and we can show that you can even introduce some small imperceptible motion to those scenes such that it allows you to run this technique. So far I talked about enhancing the resolution, but I said before, we as humans don't see everything in high resolution. So in fact, what we are doing, we are scanning our visual field using so-called saccades. So we just rapidly move from point to point. We acquire high resolution information from all around us, and then we form this kind of image of high resolution image of the world. And this is quite useful for showing the content on the screens and saving some computation, because nowadays you can use eye trackers which tell you essentially where we are looking at the scene. So what's being done is actually, and what people are working on, and are the techniques called so-called foliated rendering techniques, where you essentially, if you see this red cross, maybe it's not super well visible, but this is the location where the person is looking at, and that's the location where you provide high resolution, high quality, and everywhere else you're free to actually provide lower resolution. So one problem with this technique is the latency introduced by the system. So what actually happens, I told you that we scan the image using those saccades that go fast from place to place. So what actually happens is that when such a saccade is started, we render at the beginning high resolution maybe here, and then we move our eyes to different location in the image, and then we would like this area to be high resolution, but because of the latency of the system, the region which is high resolution is lagging behind. And this is not maybe a problem during the saccade, because there is something which is called saccadic suppression, which makes us essentially less sensitive to those things when we move our eyes quickly. But at the end of this motion, when we actually focus at a certain position, we resolve our vision, we see high quality content, but then this lag introduces this very annoying popping artifact. So we look into this problem, and we again try to do experiment, look how those saccades look like. We started modeling them depending on the distance that you travel with your saccade. And it turned out that you can actually model those things so accurately that what you can do is when the saccade starts, you can at this moment predict when it's gonna to end. So the trick is, instead of following this trajectory of the eye during the saccade, you immediately display the high resolution content at the final location. So again, during the saccade, nothing really happens because we have kind of blurry vision, so to say. But at the end, when the saccade ends, we already have very high resolution, very high quality content there. And with this, so this was a very recent project that we finished. And with this, I would like to talk a bit more about other kinds of displays, in particular stereoscopic displays. And what I will be showing here is not only stereoscopic displays that you maybe some of you experience in movie theaters, but also all those kind of new displays like VR and AR, and all what I'm saying here pretty much applies to them. So the stereoscopic impression is created by essentially showing two different images to both of our eyes, as we would see in the real world. And what the human brain is doing is trying to combine those images into one. And then those tiny differences between those combined images, we call them disparities, and they lead to this strong stereoscopic impression. However, this is not that simple. The problem is that this stereoscopic illusion is one big fake, right? Because we show a stereoscope 3D content on a flat screen. And we do it essentially by showing the same object in two different locations to both eyes. And then by combining those images, we actually see this kind of flying maybe behind or in front of the screen object. The problem is, however, that we still verge on this object, so we focus on this object in a sense, but we still have the content which is displayed on the display, and we have to focus our lenses in our eyes such that we see this image sharp at the screen. And this disagreement between those things two things is essentially the source of so-called this visual discomfort and the sickness that you can experience if you go to cinema. And it's not that bad, because in some area around the screen, you can actually tolerate it. So if the movie is well done and you're not too sensitive, it will work and you will not get sick. However, what you have to do, if you have a content, this is just a rendering, but also this is done for movies. If you have a content and you want to show some objects in front and behind the screen, usually what you have to do, you have to compress, kind of squish your scene such that it doesn't go beyond this comfort zone. And here again, the trick is with this kind of non-uniform quality across our visual field. As I told you, when you focus on certain object, you don't see much of the details in your periphery, but it's also true for depth. You don't see much of the depth variation in your periphery. So what you can do, you can first of all, you can actually move the scene such that the object that you're looking at is aligned with the screen. So then there's this kind of disagreement between where you focus and where your lenses are focusing is minimized. But moreover, what you can do, you can restore the depth information at the object where you're looking at and kind of taking back the depth from the object that are kind of in the periphery. And this also turns out to work very well. You can also, when you change the viewing position, you can, repeat the same procedure for the other object that you are currently looking at. At the end, this modeling and rendering, everything can happen in real time. And we demonstrated that you can run it on, for example, VR headsets, where you on the fly change this depth. Maybe you see this kind of ghosting, red cyan ghosting. Essentially, those are the positions where the people are looking, or the person is looking, and then we on the fly can adjust this content. So this was essentially something that was preventing the sickness and this kind of fighting this, we call it vergence accommodation conflict. But we also looked into how you can actually improve displays to mitigate this problem. And it turns out that this is, our recent design of the display. It's, it's very research stage thing, but actually you can come up with those displays that address this accommodation very accurately. So as you can see on this video, maybe we'll show it again, when the camera looks through those lenses, we actually can move the object back and forth, and we can actually focus at the right distance. Okay, so far I talked about displays, which provide a visual stimulation, but we also look into how we can apply similar techniques in the context of digital fabrication. And here essentially, digital fabrication, and especially additive manufacturing, which was developing very rapidly recently, allows us to create all those very interesting and triggering shapes with a huge variability of materials. And what allows us to actually create those objects is the fact that we have those multi-material printers. So whenever we want to print something, the object that we print is actually subdivided into tiny, tiny voxels, and each voxel can be a different material. Now, the question is how we determine the assignment of those materials to those tiny voxels. And this is, in the context of computational fabrication, this is usually done by running optimization, which takes as an input the geometry, some physical properties that we want to reproduce, and then runs some optimization in the background, and then and then figure out the assignment for us. The problem, however, is that we have really billions of those tiny pixels, those voxels, and it's very hard to address, in the optimization, at the optimization stage, all of those tiny voxels. So what we've been working at some point is some smart representations that are tailored to those application and computational fabrication, which provide a subdivision of those objects such that we can have few parameters that this optimization is working on. And those are some results that we obtained. So we show that you can very easily optimize for the appearance. You can also optimize for some optical properties. So this is a piece that we optimize. When the light shines through this object, it creates this Einstein image on the wall. But the main limitation of the 3D printing is the fact that whenever you want to print something, all the objects that you actually are printing are not the object that you want to print. So, if you pick up this shoe, you kind of have to figure out how you can change it such that you can actually print it on a printer. So you have to map it to the space of printable objects. And at this point, what is critical is when you run the optimization, what kind of error metric you're using for running this optimization. So this is something that we are looking into this in two contexts. So in the context of appearance reproduction, so those things are printed, but they look actually quite good. So they are materials that, wood and some velvet. So this is one kind of target application of this manufacturing for us. And the other is a, tactile reproduction, where we actually try to fabricate things that feel like some real material. And we address this first in the context of elastic objects. So if you think of an elastic object and the way you specify the elasticity, you essentially record how this, I don't see the animation here, that's maybe the, oh, I see there. So you essentially analyze how this duck in this case squishes, and then you try to reproduce this behavior. The problem, however, is that we as humans, we don't really measure physical values, but we have our way of justifying the compliance properties. So again, to kind of figure out how people do it and how we can use for fabrication, we run some experiments where we ask people to poke different things, we ask them different questions, how similar, how different they are. And based on this, we are able to essentially, again, create a computational model that takes something from physics. So it takes physics-based simulation. It takes kind of modes on interaction, so how we interact with the object, and can create this computational model for perceived compliance, what we call. And what this allows us to do is, if we are with the task of reproducing certain object, and we have some choice of materials that we can choose from, we can actually put all these things to this kind of printable space, but this space has an important features such that we can easily measure the perceived differences between those objects. So we can measure a distance, and this distance will roughly correspond to something that you would say when I give you these objects to compare. And in such a scenario, if we have such a space, we can just always pick the closest material that gives us this behavior. And even more recently, we're essentially applying kind of the same strategies to traditional drawing and digital drawing. So in digital drawing is cool because you have many functionalities. You just use one stylus and tablet to do this art. But on the other hand, you lose the subjective feeling and subjective haptic feedback that you get, and also you lose the controllable strokes. So we try to kind of think how we can bring those haptic, this haptic feedback to digital drawing. And very similarly as before, we also, we again have to run some experiments where people are essentially trying different fabricated materials. We have a custom physical-based simulation, and we again have, in this case, a bit more complex space where we can always put new things and we can compare the differences. And at the end, we can, for example, fabricate, or we have this fabrication pipeline for custom drawing styling. So just to conclude, I hope I gave you some glimpse of my research, and I convinced you that having this perception in the loop and having this computation makes a lot of sense. And at the end, I would like to acknowledge, all the collaborators, students that work with me, and external collaborators, partners, and supporters that support this kind of research. Thank you.